This is an exam review for normal and tangential coordinates. Normal and tangential coordinates. This is section 13.5 in your book. And let's take a look at this first problem. It says determine the maximum constant speed at which the 2 megagram car can travel over the crest of the hill at A without leaving the surface of the road. Neglect the size of the car in the calculations. So one thing to keep in mind, if you're going around a curve like this, we're going to have to take into account normal acceleration. And we're given the equation of the hill, as you can see there. So let's take a look at this. So we're going to need to eventually find the normal acceleration. And so we're going to need to know the radius of curvature. And we're given the equation of the hill y equal 20. If you multiply it through, if you actually multiply that through and divide out the 10,000, you end up getting 20 minus x squared divided by 500. And if you evaluate this at x equals 0, this comes out to be 20. And since we're in meters, that must be 20 meters. Now we have to take the first derivative, dy dx. And we take the derivative, that goes away. A 2 will come down, now divide into the denominator. There'll be minus x over 250, evaluated at x equals 0. And that's going to actually give us 0. And remember, the second derivative is going to be the slope. And of course, that makes sense because you can see at the crest of the hill, the slope is going to be 0. It's going to be horizontal. Then take another derivative. Like this. And we'll evaluate that at 0. Of course, it's going to be the same no matter where it's evaluated, minus 1 over 250. Then to find the radius of curvature, we use our little equation. 1 plus dy dx squared 3/2 over the second derivative, the absolute value of that. Excuse me, that should be dy. Like this. And substitute all of our values. 1 plus 0 squared, the 3/2. Obviously, the numerator is going to be 1. And the denominator's absolute value, negative 1 over 250. And this ends up being 250 meters. Like that. So now we can find out what these forces are. And so we're here at the top of the hill. We have the car. And it's 2 megagrams, which is 2,000 kilograms. So the force down is going to be 9.81. And that's going to be 19,620 newtons. And then the normal will be up this way. And of course, yes, the normal is going to be in that direction. So let's sum the forces in the normal direction. And that's going to be, so if we sum them in the normal direction, we're going to, remember, usually we call any force that's towards the center rotation, we call that positive. And so we'll call towards the center rotation here positive. And so we're going to have our normal, and actually it's going to be a negative normal since that's pushing upward, plus 19,620 newtons equals 2,000 kilograms. Velocity squared. Remember, the normal acceleration is velocity squared over rho. We found rho to be 250. Like this. And of course, for the car is going to leave the road whenever this comes zero. Remember, it'll separate. Long as there's an upward force, it's going to stay on the road. But in other words, an upward reaction. But if this ever goes to zero, it's going to separate. So that'll be the point we're interested in when that's zero. And if you solve this, you're going to get velocity is 49.52 meters per second. Next, let's take a look at problem number 2. It says an 8-kilogram sack slides down the smooth ramp. If it has a speed of 1.5 meters per second when y is equal to 0.2, determine the normal reaction the ramp exerts on the sack and the rate of increase in the speed at that instant. Now, one thing to notice here, wants to know when y is equal to 0.2, it wants to know the information at that point. Now, if you look at the equation, that when y is equal to 0.2, that's going to be when x is 0. In other words, if you look at that equation, this is going to be 0.2 when x is 0. That'll make that 0.2. So let's go through now. These steps are exactly the same as the previous problem to find the radius of curvature. So I wrote them out ahead of time. I'm not going to spend too much time on these because they're very exactly the same as the last problem. But if you want to write these down, you can stop the recording and write them down. So now we need to find out what's going on at the point they're interested in. So you have this sack, going down something like this. And it's at this point right here. And it's 8 kilograms. So 8 kilograms times 9.81 is going to give us 78.43 newtons is what it's applying down here. Now the question is, at what angle is this normal force going to be coming up? Now, one thing that we are given, we were able to calculate the slope up here, so we can get an idea of what we have here. So again, the slope was 0.2. So the slope again, remember the slope is rise over run, so you can think of that as being 0.2 rise and 1 run. That would be the same as the slope of 0.2. And then you could calculate the angle here. And what we need for that would be the tangent, I guess. So the tangent of theta is opposite over adjacent. And when you put that in your calculator, it will give you a theta of around 11.31 degrees, like that. And now from the geometry here, the way it works out, if this is theta here, this will also be theta here, like that. And so let's sum the forces in the normal direction. And actually, we may need to mention, let's see, one more thing. So again, if that is theta, and let's say if we have something like here, then this also has to be theta over here. So again, let's sum the force in the normal direction. It'd be like going in this direction. And call positive in that direction. We're going to have our normal. Then minus this force down here. But again, we want to resolve it into the normal direction. And that's going to be at an angle theta. So that's going to be our 78.48. So that's going to be, then again, to get in the normal, it's going to be cosine of theta, or cosine of 11.31 degrees equal MA. That's going to be 8 kilograms. The velocity we're told was 1.5. And this was 5 point, the radius curvature 5.303. So the normal is going to be 80.35 newtons, like this. And that's all we need to do for this problem. It won't be necessary to find that an increase in speed. That's not really what we need to do right now, so we can stop right there. Take a look at this problem. The collar A, having a mass of 0.75 kilograms, is attached to a spring having a stiffness K of 200 Newton over meters. When the rod BC rotates about the vertical axis, the collar slides outward along the smooth rod DE. If the spring is unstretched when S is equal to 0, determine the constant speed of the collar in order that S is 100 millimeters. And you can see from the picture that S is measured from the center. And so we want S to be 100 millimeters or 0.1 meters. And we want to find the speed that'll keep the collar at that point. So if we look at this from above, we have a situation something like this. It's spinning about the center, and then we want to find out what it's going to take to keep this about 0.1 meter from the center. Or we can maybe make a little free body diagram over here. And of course, we have a spring force. And then that's going to be spring force. Of course, that's going to be K times S, or delta S. And our K was 200 Newton meters. And our S was 0.1. So the spring is going to put about 20 newtons of force on the object. And of course, it's going to be rotating about this center. So let's sum the forces in the normal direction. Again, this is kind of pulling towards the center. And of course, towards the center, we usually count as positive. And we'll call this positive. And so again, the only force we have actually acting on this is the spring force of 20 newtons. And we have the mass is going to be, I forget what that was. Let me just check here. The mass was 0.75 kilograms. And now for the normal acceleration, of course, that's going to be velocity squared over rho. But we know that rho is 0.1 meters. That's how far it's off the center. Like this. And that's really all we need. And this is going to be 1.633 meters per second, like that. So again, there's a pretty common problem if something's rotating about a center. You want to sum the forces in the normal direction. If you have spring forces, count those and calculate your velocity. Next, take a look at this problem here. Cartons are moving along an assembly line at a constant speed of 8 meters per second. And determine the smallest radius of curvature rho so that the cartons do not slip. Coefficient of static kinetic friction between a carton and conveyor are 0.7 and 0.5 respectively. So we have to find the smallest rho so that there's no slippage. And so let's take a look at that. Now it's important to notice, again, if we're going in a circular motion and doing something like this where we're dealing with friction, it doesn't really matter if the object is moving or the disc on which the object is sitting is moving. In fact, the next problem we'll look at the case where the disc is moving and the object is stationary, but they're all handled the same way. So let's take a look at this one. Again, you have this box, going around in a circle, or at least around a curve, like this. And we want to find the radius of curvature rho. Now, if you look at the side view of the box, we're going to need to look at that to get an idea what the friction is going to be. So again, the box is 5 kilograms times 9.81. And that's about 49.05 newtons. And there's really no other forces because the box isn't moving horizontally, vertically or anything. So again, looking for the side view, that means the reaction here is going to also be 49.05. And then the friction would keep it from going off. So the friction is going to be like in this direction, like this. So again, this is kind of just a free body diagram, side view. Now again, looking at this picture, so that like this was from above, looking down, and then this is from the side. Now the radius of curvature would be like this. And so let's take a look at this problem. Again, the friction is going to resist. And now one thing, let's note here, the friction, of course, is going to be mu times this normal. Now they gave us mu for the two cases, the static and the kinetic friction, but actually the box is not sliding. It's not sliding along the conveyor. In other words, it's not slipping, what I'm trying to say. So really the friction we're interested in is the kinetic friction. So excuse me, the static friction, because it's staying on course, it's not slipping. So we're going to use the static. And then the normal is 49.05. And that comes out to be 34.33. And let me just round it off, 33.5 newtons, like that. So then sum the forces in the normal direction, the way we've been doing. Again, we're almost always going to do that with these rotating problems. And then the only force that we have is friction. And so friction will be, and I'm not sure what sign we want to put that on. It is going to be keeping it from going off, though. It's going to be in towards this. Yeah, so it'll be going towards the center. So the friction force will be towards the center rotation. So we'll keep that positive. So let me just note that we have here. That's the only force. And of course, the mass. And this is going to be the velocity squared over rho. And the friction force, 34.34. And the mass was what, 5 kilograms. And the velocity, we're told that the velocity is 8 meters per second. And the rho is the only unknown. And when you solve for rho, you get something like 9.32 meters. So that's going to be the minimum radius required to keep the carton from slipping. Next, let's take a look at this problem. Suppose the static friction between the block and the turntable is 0.3. The block weighs 4 pounds. Find the maximum velocity so that the block does not slip. So let's take a look at this one. Now, again, it's handled in pretty much the same way as the previous one. So we have the again, if you look from above, we have this thing going around like this. And then we want to find the maximum velocity so that the block does not slip. Now, they don't actually give us the value of R, so we'll just write down R. And there's going to, again, from the top view, from above, like this. And again, from the side, it's going to look something like this. Again, we have our 4 pounds down, and of course, there's no other forces in the vertical direction, so the reaction has to be 4 pounds. And there's going to be a friction force here. And of course, that's always mu times NC. In this case, we're told that mu was 0.3. And so it looks like this is going to be like 1.2 pounds. Like this. And again, the R is kind of in this direction. So again, let's just sum the forces in the normal direction. And again, all we have is a friction. Again, friction is towards the center, so that's positive. So let me just write this down. And then, of course, this could be velocity squared over rho. And we have 1.2 pounds. And again, now when we put the mass in, we have to divide that by 32.2 or 32.17. And velocity squared. And then again, our rays of curvature just are, they don't give us a specific number. Oh, and I made a mistake. I just realized the mass here should be 4 pounds, not 1.2. The mass is 4 pounds. So 4 divided by 32.2. And when we solve for the velocity and work this all through, we get velocity squared equal to 9.66 R, or velocity is equal to 3.11 square root of R, like that.